So maybe we get slowly started. Welcome to the second workshop of today. I hope you can hear me right now. Do I get a thumbs up maybe?
Yeah. Yes.
Okay, cool, thank you. Welcome to the second workshop today, which is also the second workshop which is coming from the Biomedical Center of the Ludwig-Maximilians-Universität in Munich in Germany, at least most parts of it. For this workshop, we have teamed up with Daniel Smeets, who is now working with Leica, where he is advanced workflow specialist confocal microscopy. The topic of this workshop is Tau-STED in specifically, but also STED and a combination of STED and FLIM in general, mostly about Tau-STED, which is a technique that, to say it very easily, improves resolution. Daniel has already a talk prepared for that, of course, because he's the specialist from Leica concerning this topic. So that's very nice for us, so that we don't have to think about it too much, because we got the talk presented here. And also he will then present some data. This will be a combination of talk, of a live session, and of recorded sessions. One of the reasons for the recorded sessions is that right now, under Corona conditions, it's maybe, let's say, not recommended to cram too many people into one room. The other reason is that we will see some live cell data, and for that we would have to heat up the microscope from room temperature to 37 degrees. That takes quite some time, so we couldn't do it all in one session. So that's also then a recorded part. Okay, did I miss anything? Daniel, Mariano? If not, Daniel, please go ahead and let's have an introduction to Taustead and what that actually is.
All right, thank you very much, Steffen, first of all, for the kind introduction. Thank you very much for attending our session here about Taustead. And also thank you again for the organizers to making all this happen. So until now, you have heard quite a lot of applications and ideas of how you could make use of lifetime information, different areas of microscopy. All right. Now in this session, I would like to give you a little bit a different spin on the lifetime topic, and would like to show you, as Steffen has nicely explained, how you can make use of that in STED microscopy. Before I go into further details here, sorry, that was Zoom. Okay, now my legal colleagues asked me to kindly let you know that please don't take your own recordings of the session. Steffen and the organizers are recording all this material, and of course we can then make it available to you afterwards. So having said that, let's have a little bit a look into how we can break up our session here this afternoon, so that we have a little bit a guideline to follow. So right now we're in the middle of my presentation part, which I wanted to start with. And please, if you have any questions, let me know right away. It's a bit difficult for me to follow the chat window, or we can have questions, of course, at the end of this presentation as well. After that, as Steffen said, we have a combination of recorded sessions, which are actually recorded on Steffen's and Mariano's system at the BMC just a couple of weeks back, due to Corona reasons and others that I don't like to go into detail right now. But we will first start with how you can use Taustead on fixed samples. And it's not a full block of 1 hour. We have also chopped this up into smaller segments. And although it is recorded, which makes it unfortunately less interactive than the brilliant presentation from Mariano this morning, at the end of each block, there's still the opportunity for you to ask your questions, of course. Then after this first part, we switch on to using Taustead with living samples, which I have also pre-recorded previously. And then at the end, we can have a common session for questions and answers again, if you have then still more questions on your mind. So let's get started here with the first one. And as probably many of you know, super resolution microscopy in general has been awarded with the Nobel Prize in chemistry already in the year 2014. And actually at that time, during the award ceremony, one of the committee members that you can see here, Mans Ehrenberg, he mentioned in his speech that STED and other super resolution methods got awarded with the Nobel Prize for their realistic quantitative descriptions at the nanoscale resolution of the dynamics of the complex multidimensional molecular biological processes that define the phenotypes of all life forms. Wow, that's a lot of information, basically packs everything that we want in microscopy in one sentence. And of course, all this is true for super resolution methods and specifically for STED microscopy, of course. Otherwise, they wouldn't have awarded it with the Nobel Prize. However, if we are brutally honest to ourselves, then the dynamics part has been lacking a little bit behind in super resolution microscopy in general. And this is where now FLIM comes into play. If we combine FLIM microscopy together with STED, that allows us to be able to lower the resolution, to lower the depletion laser powers at the same resolution, which makes it then much more usable for live cell imaging. And that then of turn is then a closer situation to your real natural sample state, which gets you then closer to the truth in your samples. So let's start with lifetime. And don't worry, you have heard this many times. So here I just would like to mention that lifetime information, as you have seen with Mariano this morning, in our Leica case means that we have our FALCON module that allows us now to capture not just the intensity information as you would normally do in confocal microscopy, but at the same time, in parallel, we can now also read out the lifetime information. And again, you have heard many options of how this is useful. And now I would like to draw your attention to the fact that in general, with having the access to the lifetime information, we can of course measure lifetimes, but we can also see changes in lifetimes very easily. And here it makes it, or it's really necessary to have a fast FLIM system in order to be able to measure that on the fly, also during your regular scanning conditions that you use. And in our case, changes of the lifetime, in the case of STED, means that as soon as we add a STED depletion laser, we are now changing the normal lifetime distribution of our fluorophores. And if you look at this Jablonski diagram, if there's no STED, you have your normal excitation emission process going on. As soon as we add the STED laser, which of course stands for stimulated emission depletion, means that we are forcing our excited fluorophores back to the non-fluorescent state, and we do that faster than they would normally do that. So actually what we do is we shorten the lifetime as soon as we add the STED laser. So now let's put all components together. So in STED microscopy, what you need is you need an excitation laser. And in our case, this would be the white light laser, which is also a pulsed laser. Second, you need a STED depletion laser. Everywhere where you have the STED depletion laser present, you are switching off your fluorescence again. So that happens everywhere, apart from the very center of this donut shape. And that effectively gives us now a much smaller point spread function, which has then a higher resolution, which makes STED the super resolution method that you know. And the size of this point spread function down here now can be tuned. Depends on how much laser you put into your STED donut, what is the shape of your STED laser. But classically, what you have now measured is an intensity-based image, an intensity-based STED PSF. Now, in the case of Taustead, what we do is we give our STED system an additional tool in our toolbox, and we allow it now to measure also the lifetime. And if we do that, and if we now look at our STED PSF, we can see that, and we can discriminate now the very center from the periphery thanks to the lifetime. in the very center of the STED PSF, this is where you would have the longest lifetimes, because this is where you are the furthest away from the STED laser. This is where your fluorophores are most unaffected. The further you go out to the periphery, the more also the competing effect of the STED laser comes into play, and the shorter and shorter the lifetimes will become, until ultimately they will be zero, because out there, this is where complete depletion will take place. So giving now the FLIM capability to our STED system allows us now, like a stopwatch, to really measure on the pixel by pixel base. Are we dealing here with a high resolution photon, which is coming from the very center, or are we dealing with a low resolution photon coming from the periphery? And we can do that in parallel now during the normal scanning process, during a normal and also fast scanning conditions. And this is what we now call Taustead. So this is the combination now of our FALCON module onto our STED systems. It will give you three main advantages. First is that you, by doing this, can improve the resolution, or you could at the same time also lower your laser powers by around a third and still get them to the same resolution improvement. So that, of course, is then most beneficial if we then also talk about live cell imaging, which we will also show you now as one part of the hands-on session. The last benefit would be that, and Mariano explained this also brilliantly and showed this also, that we can now combine dyes which are optimal for STED, but which normally you cannot separate spectrally. So we can add more STED dyes and still keep the same depletion laser active. So with Taustead, this is not our first STED system at Leica. We actually have now a history of 15 years in total in STED microscopy. And with the Taustead, we are just adding the next step to that and building onto this. And here's an example that we also briefly discussed. So what you see here is single molecule RNA fish and Drosophila larvae, which just shows you already the nice multicolor options that we have. And here you don't have the problem that Stefan mentioned with the that you're running out of species for your secondary antibodies or primary antibodies, because this is an example where the users here use the direct labeling of their probes. Also, we can not just look at flat samples, we can actually also have a nice STED image deep within the tissue. Here in this case, this is a cleared kidney, part of a kidney, glomerulus, which is actually more than 100 micrometer thick, and where we can nicely get a nice resolution improvement throughout the whole depth of the sample. Live cell microscopy is something that our STED systems are also well adjusted for. You can have a resonance scanner for fast scanning, which makes the whole process much more gentle compared to scanning slowly. And we also have dedicated water objectives, for instance, which you can really use to also adjust to your sample. And this then allows you to do experiments like this. So here you see a living T cell growing in suspension, which has been imaged both with confocal and in STED in this case, as you see. So that is the first component that you need, the STED system, which I now mentioned a couple of examples. Second one is that we add our FALCON module, which allows us now to measure the FLIM information in the sub-second range. And therefore, we can do this really on the fly in parallel to our normal scanning conditions. Third component and last one that you need is phasor analysis. Mariano brilliantly explained phasor this morning. And in the Taustead process, this is what we are using. We are looking at our lifetimes in the phasor plot, and then you can see what happens as soon as you switch on the STED laser. So in the normal confocal phasor, your lifetime has a certain distribution. As soon as you activate STED, that distribution is changed because we are shortening our lifetimes. However, we are not doing that uniformly, but we are creating so-called trajectory, so a gradient here, which goes from long lifetimes to short lifetimes. And we know that the long lifetimes are the ones with the high resolution. Third is that we have all the rest, all the other stuff around our dye clouds here, which is actually not affected at all by absence or presence of the STED laser. And this is all the other stuff that is maybe fluorescing in your sample that you actually don't want to have in your image. So this you can also nicely identify here and just get rid of in your final image. This is something that the whole process of adding FLIM and STED that has been described in a couple of publications already a couple of years back. First starting around the group of Enrico Carton around 2015, who showed that when you add lifetime information to STED, that gives you an enhanced resolution and allows you also to go lower with your depletion laser powers, which is also, here's another publication which explains the use of the phasor plot analysis in this whole approach. So to summarize, these are the three components that we need. We give our STED system now a stopwatch, which is the FALCON, which allows it now to really, on the single pixel level, discriminate between the high and the low resolution photons. And we do that during the scanning. Then the system automatically in the background is looking at the phasor plot. It's detecting the STED trajectory, and it's also detecting where are my background contributions. And then in your final image, you will have a result which got rid of all these background components, which then of course increases signal to noise dramatically. And as we have now this gradient, we can now nicely tune how much resolution improvement we want in our final image without having to go back and acquire a new one. Actually, you can do that now in post-processing. And you can do all that at much lower light dosage. So you can go down to around just a third of the depletion laser power to still get the same resolution improvement as with pure intensity-based STED methods. So just to show you, in case you haven't noticed yet, all this is taking place inside this FALCON window in our software. There's then one Taustead button here, which we're using and which you will see later in a second. So one additional advantage, I briefly mentioned it now already, is that as we have acquired all the lifetime information anyhow in parallel with a Taustead acquisition, and you have basically a gradient, it's up to you how far you want to stretch the resolution improvement. So you can go just to the higher and higher and higher resolved pixels in the end and ignore the other ones. So you have now a tool that really allows you to tune the resolution, even in post-processing, which of course is similar if you know gated STED, for instance. There you could make like a steep cutoff and also throw away mainly the background photons. But if you then wanted to change something, you had to go and make a new acquisition. So there was no way to do that in post-processing then. And here's what I mentioned. If you compare now pure intensity-based STED, gated STED on the left side, so here you see a tubulant staining, and this has been imaged with the 660 depletion laser at 45% in this case, which then gives you a great resolution improvement. Now with Taustead, as I said, you can go down to just a third of this, just 15%, and on the other hand, keep the same excitation laser power, don't increase the excitation laser power as well, and you will end up with round about the same resolution, but with much less light that you put into your sample. And here you can also measure this. And indeed, so here we are at 89 and here we are at 85 nanometer. On the other hand, you can still go to even 100% depletion laser power, of course, if you want. And then you have even this additional tool of being able to tune the resolution. So you can also, of course, push the resolution as much as possible. And here's an example of Gatter beads, 23 nanometer beads, which we have imaged with our Taustead, and where we measure regularly. So in this case, it's 27 that was measured here, but where we can then measure, regularly measure lateral resolution of less than 30 nanometer. Of course, you can do this still all in multicolor. And you have heard now many times that there's even now more multicolor options available. And Mariano will point that out in one of his hands-on sessions now. You can now benefit from that really in live cell applications. So this really now emphasizes the dynamic aspect that I have mentioned in the very beginning, because now you can work with laser powers, which are now much more easy going to your live cells, and where you can now really go ahead and take long time series acquisitions without harming your cells. I mean, ideally, you of course do that in the longer part of the spectrum. The more redshifted you go, the less energy you put into your sample anyhow. So here you see an example of an SIR tubulin, where 10% 775 depletion laser power have been used, and where in a living cell we could then measure 48 nanometer, which is pretty good already. But it's also beneficial in the range which classically has been quite challenging, especially for live cell, which is if you go to the more green part of the spectrum. So here you see an example where the 592 laser power depletion laser has been used. Again, it's just 10% STED power. And I will also show a similar example in the hands-on session. And here we see really over 230 frames imaged continuously with a rather high speed, 1 frame per second. And we now nicely see our live cell dynamics in super resolution here. Just one point, Mariano nicely showed how you can use Phasor to separate overlapping dyes in the software. This has been improved if we talk about the latest platform that we have on the Stellaris. So what Mariano did now brilliantly manually on the Stellaris software, you can actually do that now automatically. So it's a much less clicking than what is still required, unfortunately, on the SP8. But this is simply still the continuous improvement, I would say, that is going on. And last but not least, one example where 2 dyes have been used, Star 635 and Atto 647, both of which brilliant STED dyes. However, they overlap almost completely spectrally. And here, lifetime information has been used to separate them. And actually, this was a rather crude separation. So if you do it the way Mariano showed it, you would be able to separate them much more smoothly, as you have seen. So to summarize, with Taustead, you can improve the image quality and resolution at a much lower light dosage, thanks to the combination of lifetime information and STED, because we can now really measure on the pixel level, is this a high resolution pixel or is it a low resolution pixel? You can therefore also do much longer time-lapse experiments, and we will see some examples now in the hands-on part. And especially if we talk about dyes in the green part of the spectrum, like a GFP or a neon green, those will be much more easy to use now with STED than they have been in the past. You can, at the same time, thanks to the Phasor analysis, easily and without any fitting, identify uncorrelated background, so lifetimes which are not affected by the absence of presence of your STED laser, and which can therefore easily be removed from your image to improve signal-to-noise ratio. And you can also combine things like FLIM thread or multicolor separation using the lifetime, also in STED microscopy. And this will be something that Mariano is going to show you also. So with this, I'm at the end of the first presentation part. And I would be very happy to take a few questions. So I think we have 5 minutes now for some questions before we can move to the first hands-on part. And who would like to have the first question? I didn't follow the chat, so maybe
you have a couple of questions in the chat, so
okay.
Can you see it?
Let me see. Where is it?
Normally, you need to go to the menu in share screen to more, and then you have chat.
Right. Here. Okay. Got it now. So it starts on the top. Is that the first one, or did I miss something? So fast.
Yeah, the first one is from Jessica Valley. That she's asking that you say Tau-STED allows to lower your laser powers. Is that the excitation lasers rather than the STED lasers?
So thank you for the question. So you want to know if it's only the excitation part or also the depletion part, because of course for STED microscopy both add to the laser light that you put into your sample. And I totally agree. This is of course crucial if we talk about especially live cell STED or also large volume STED, that in total we lower the amount of light that you put into your sample. So what I mentioned there is that you can reduce your depletion laser power to around a third of the original one, still get a comparable resolution improvement as you would have gotten with pure intensity-based STED. So that is at a third of the depletion laser power and the same excitation laser power as opposed to pure confocal imaging. You can get a nice resolution improvement in the range that you know from your pure intensity-based STED. If on the other hand you use the same depletion laser power as before, you can push the resolution even more. I don't know if that fully answered your question, but we will also talk about this actually in the hands-on part a bit more.
Okay, so there are other questions. So the second one is how Taustead, okay, I would say how Taustead allows you to reduce or to lower the laser power needed. But so if you can say a couple of words.
Yeah, so that is we're going more into the direction of how this is possible. And if you remember, I briefly showed in the beginning that as we are now measuring the lifetime distribution in parallel to our normal scanning, this gives us now the opportunity to discriminate between the very center of the STED PSF as opposed to the periphery. So the more you go to the center of the PSF, the less affected those lifetimes will be by the STED laser actually, which means that those are the ones which have the highest resolution. Yeah, at the same time as the one with the longest lifetime. The shorter the lifetime, the more that means you're affected by the STED laser already. That means the more you're already at the periphery of your PSF. And that's where the shorter lifetimes are. So by looking at the lifetime distribution, you have now really an additional tool to discriminate resolution instead, which is great. So,
okay, so you have another question. What is the sample depth that you can measure using Taustead? So how deep can you go?
Okay, so thanks for that question. That yeah, goes in the direction of one example that I have shown in the presentation just now. So of course you want to ideally be able to not just image flat cells, which is actually what we are doing now in the hands-on part, but you would like to have a resolution improvement also deeper within your samples or a thicker specimen. And I showed this one example of the cleared glomeruli in a kidney. Of course, there would be other examples as well. In principle, what we can do is we have a glycerol objective, which makes then the whole PSF much more adjusted to tissues, and especially thick tissues, which also has a motorized correction color, which means that you can also adjust it to different Z positions, different depths in your sample. And then you can also get a nice resolution improvement deeper in your sample. In principle, the lifetime is not affected by how deep you are in your sample. Lifetime, resolution, of course. I mean, if you have a very scattering tissue, you have to keep in mind that also your emitted fluorescence needs to come out of your sample again. And the more scattering you have, the more that will reduce then your resolution, of course. But in principle, there are good ways how to also work deeper in your sample. So
there is Another question, I'll say another question is, if Taustead, if the laser power is decreased, is the exposure time of the samples increased than usual, or to get a higher resolution image? No, wait, I'm going to read it again. So if the laser power is decreased, is the exposure time on the samples increased than usual to get a resolution image or not? So meaning that you need to increase your pixel dwell time without STED or not, as opposed to normal STED.
So let me rephrase, or let me, for myself, repeat the question. So if Taustead, if the laser power is decreased, yeah, exposure time on sample increased. I'm not sure if I get the question correctly. So in principle, the exposure time or the pixel dwell time is, of course, independent of your STED laser power. You have options, and maybe this is where the question is going to. You have, of course, options to change the exposure time, so the pixel dwell time. So you can change scanning speed. You can change how much repetitions you want to do. You can also work with the resonance scanner for high-speed acquisitions. And that, of course, will affect mainly your signal-to-noise ratio. But resolution as such won't be affected by that. I don't know if this answered your question or if I got it correctly, but this is what I would say now here. So, okay, maybe we look at the next one.
Yeah, apparently I'll say.
Okay, one comment from Hella. Will you please
comment.
improve the phasor analysis for SB8 systems as well? Thank you, Hella, for that comment. That's definitely something that I would love to see as well. I mean, at the moment, this is a very new feature that this is possible, which is why it's for the moment implemented on the latest platform only in that software, where we actually also have reworked the architecture of the software quite a lot compared to the SB8 architecture. So this is something that I totally agree. This would be good, also personally for me, working a lot at the BMC. But yeah, it's unfortunately nothing that is super easy to implement in a short time. So I hope, like you do, unfortunately, I don't have any more concrete information of when and how that will happen. Okay, could you?
Yeah.
So maybe the last question now, for now, or so there's one more from Tanmay. Could you please elaborate why you would want to collect the short lifetime photons at the periphery out of the donut? So that's a question that goes in the direction of why is that actually needed to do that? Why would you even want the short lifetime photons in there? Well, the answer to that is you don't actually want that. So in STED microscopy, the smaller your STED point spread function, the higher the resolution will be. And in classical intensity-based STED, you try to achieve that by either going to higher depletion laser powers, which then make that volume simply smaller, or also to use the gating functionality to cut off very early arrival times, but which then mainly removed the uncorrelated background from the image. So you simply had no other means of apart from these two things. Whereas now we can really see in parallel, thanks to the lifetime information that we have for every pixel, is this now a high resolution or is this a low resolution pixel? And if you want to tune to an as high resolution as possible, then of course you want to get rid of all the shorter lifetimes. If you also want to consider a little bit signal to noise ratio, then you want to include more also of the shorter lifetimes and sacrifice then maybe a little bit on the resolution. But the good thing is you can also decide that once you already have your data. You don't have to acquire a new experiment for that. Okay, so thank you very much for all the good questions and valuable questions in this regard. Just a bit slow in reading in parallel, so apologies for that. So let's see, is there one more?
I think that's it for now.
Okay, so thanks again for listening, and I think now we can move over to the first hands-on part. We will start with myself talking again, sitting on the same system that Mariano is now sitting in front of. However, a few weeks back, the first part of that will be something like 26 minutes long. And yeah, as it's recorded, unfortunately, I don't have the option to do it as interactive as Mariano did it now.
Yeah, no worries.
Anyhow, we can, after that first block, take all your questions, of course, and then maybe we can also see something on the system in live.
Yeah, for now, I'll say we're just going to make you a little tour of the microscope like we did in the beginning.
Yeah, okay, please.
So, I hope you all can hear me. So this is why you didn't see me before. The webcams are all in the microscope right now.
Stefan, it's a bit difficult to hear you.
Mariano is trying his best of holding the microphone very close to me.
Okay.
Other than that, I only can try to shout.
And now it's better.
Here we have the actual microscope. That's DMI8 with the incubation box around it, so that we can keep the temperature for the live cell recordings. However, it turned out that it's helpful not only for live cell recordings, but just to keep the temperature stable on the microscope itself. If we have the temperature on, in this case, on 22 degrees, it's a little bit more. I'm not sure you can see that here on the ice cube. Right now it's 22.7 degrees. It just helps to have the box around so that you do not have as much thermal variation that you otherwise might have. So left to it, we have all the temperature equipment, chiller and heating, depending on what we need. And further left, we have a rack of lasers, which is over there somewhere, with the bright light laser on top and then the STED lasers on below. And right to the microscope, we again have two screens, of which we later on will be able to share only one of them during the Zoom session. And that's then the, let's say, usual SP8 inverted microscope setup that we have here. That it is a STED microscope. You can see there on the left to the microscope, because there is a little box attached to it which says STED. So this is how you recognize them if you can't fire up the software. Yeah, and I guess that's the most of the things that we can show here. So any questions on the setup of the microscope? Well, if not. And if not, I guess we just switch webcams again and start with the session.
Hello, everybody, and welcome to our hands-on session around Tau-STED. I'm sitting right now in front of an SP8 confocal with Tau-STED capability, and the sample that you're looking at here right now are fixed COS7 cells, which are labeled with a star 635P labeled antibody against a nuclear pore protein. For those of you who are not familiar with our SP8 interface, I would just like to give you a quick overview what we are looking at here right now. We do have a very flexible excitation source, which is called a white light laser, which actually provides you with the possibility to choose any excitation wavelength from within the range of 470 up until 670 nanometer. And you can do that with a precision of 1 nanometer, and actually also choose up to 8 different excitation wavelengths at the same time. Right now, I'm of course working only with one dye, so I can remove the additional laser lines and just optimize my excitation laser to the dye that I'm working with right now to make sure that I really optimally hit it at the peak of its excitation, which on the other hand allows me to really use as little laser power as possible for this dye. On the detection side of things, we also have a unique emission filter-free detection concept, which consists of two components. First, we're using a glass prism to separate all the emission light, which is coming back through the objective from your sample into its spectral components, like a rainbow. And then as a second step, we have up to 5 individual detectors in our system, and each one of those detectors is equipped with so-called spectral sliders, which allow you to, again, with 1 nanometer precision, choose which part of the spectrum should actually arrive at the detector that is sitting behind those sliders. And all that, as I mentioned, without the use of any fixed emission filters, which makes it a more efficient way of detecting fluorescence signal, making sure that you really capture all of your precious photons. And it makes it also an extremely flexible solution, as we are not stuck to the equipped filter sets that you have on that system. So having said that, I did set up my acquisition settings already for the dye that we're looking at here right now. If I click on the live button, we do get a live preview of our sample at the current position. I can change the Z position already here, as you can see. And if I would like to get an idea of how neighboring areas in my sample look like, we do have a tool in our software which is called the Navigator, which you can find up here, which, as the name suggests, allows you to navigate freely through your sample and find the best suiting position for your Taustead acquisition, for example. So if I click on this Navigator button, you can see we are entering a new screen, which is this Navigator interface. And inside this Navigator interface, I also have all the acquisition settings stored over here on the left side. And if I just click the live button, the system will acquire an image with my current settings that were taken over. However, if I now use my mouse wheel, I can zoom out from my current location until ultimately I will see the entire travel range of the stage and our current position on that stage. I have the possibility to get different background images, so-called carriers, that I can use already to orientate myself. For example, a slide, which is what I'm using right now. But what I would like to show you now is that if I go back to my current position, I can start doing a so-called spiral scan, where the system would, starting from my current position, move in a spiral way around in the sample. And I can use this option to already get a pretty good idea of how different cells, in this case, in my sample look like, and to then pick the ones that I would like to image as the second step. So the system just continues acquiring here until I press the stop button. And what I can also do, if I double click somewhere into the screen, the stage will move to that position and give me a preview of that area in the sample. And if I then see interesting regions over there, I can either do another spiral acquisition, or I can also mark a certain region that I want to get a preview of to see what how my sample looks like in that corner. So I think we did find already enough interesting cells that we can now image with Taustead. So let's maybe just stay here at this one, or let's pick this one over here. If I close the Navigator, I'm back into the SP8 interface that you have now seen already. And if I click again on the live button, then we see the cell that I have marked now. We can zoom in further to the cell because we don't need to acquire a lot of area without any signal in it. And for that, there's a zoom in function over here, which I can then use to mark a certain region, and the system will then zoom to that specific location. I can still fine tune the zoom if I want to. I can of course optimize my Z position also. And now I think I have found already a nice position that I now want to take a Taustead image of. If you remember from the presentation, Taustead is the combination of our fast FLIM module, FALCON. So that's the first thing I need to activate by pressing on this FLIM button over here. Now I do get immediately access to the FLIM acquisition settings. And the second thing I need is control over my STED depletion lasers, which I get when I click here on the Activate STED panel. Now I can see all the 3 depletion lasers that I have available here on that system, and I simply choose the one that is now optimal for the dye that I'm working with. So that would be the 775 depletion laser. Let's close the window over here a little bit more. I'm adding some depletion laser power to it, 20% in this case, and I will not change the excitation laser power. However, I want to optimize now my acquisition settings. So as we want to do FLIM, I will use some repetitions. And we also need to look into our format in order to optimize our pixel size. So I will change now the pixel format to give me a small enough pixel size to capture the full resolution that I'm going to generate now. We are working with a rather short pixel dwell time here, so it's okay to do a couple of repetitions. We will still be really fast when acquiring the image at the end. But then on the other hand, really have a nice and good looking signal to noise ratio in this case. All right, now I would be ready to start, but for the sake of comparison, I want to add now also a confocal sequence so that we can compare the Taustead with the confocal image at the end. For that, I will just duplicate my current settings in a second sequence. Those should be acquired between lines, so switching the settings after every scanning line. And now if I go back to the first one, which at the moment is identical, then I will just put my depletion laser power to 0 here, which will then give me a regular confocal image as in the first sequence. And in my second sequence, I will have a STED image. All right, now I will put both windows, which I have here in front of me, on another screen, side by side on the same screen, so that you can also see them. I will, remove the viewer from the main window and make it a bit smaller and put it side by side with the FALCON window, which normally, as I said, would be located on a separate screen. Now let's hit the start button, and then inside our FALCON window, which you can see now here, we will immediately see the end result. There is a Taustead tab inside the FALCON module, which then immediately gives me access to all the Taustead options, and which, as you can see already here, during the acquisition on the fly, is creating my final Taustead image. So I have 2 channels now in this acquisition due to the 2 sequences that I have created. The left one is a pure confocal acquisition without any additional depletion laser, and the right one is a Taustead image where I have added 20% of the 775 depletion laser. And now the acquisition is finished. As I said, due to our low pixel dwell time, we're really fast in acquisition. But thanks to our sensitivity of our system, and especially the short dead time of our hybrid detectors, we can really capture all the photons here efficiently to really give me a nice high quality Taustead image. And if we now zoom in a little bit closer and compare the 2 results that we got, you can already really appreciate the great resolution enhancement that we have received now thanks to Taustead. It was also really easy to get to this result. I didn't have to change any additional settings, just add my depletion laser power and a few repetition and make sure that the pixel size was correct. and then I already arrive here at this result, which, yeah, apart from the really high resolution that you can see here, also has an extremely nice signal to noise ratio, and we can really also differentiate our signal really well from the background. And this is due to the way of how Taustead works. I will go in a little bit more detail about that in a second, but just to show you what kind of options you have now in here in the Taustead module, you can see that there are two additional sliders down there. One is called Tau strength, which at the moment is at the default value of 100. And this value has been chosen in a way that you are always creating a good result with any kind of circumstances. However, if you have a really high signal to noise ratio and a good photon count, as we actually have in our image here right now, you can then in post-processing increase this this Tau strength slider to really also enhance the resolution even further. So as you can see, if I do that, I really am able to really significantly get higher resolution out of my already acquired data without having to go back and acquire it a second time. So this is what this Taustead slider is doing. There is a second one called Denoise, which if you zoom in closely, you can see what it's doing. So again, the default value of the slider is 50. If you want to create really the publication result when you come here to the system, you can just pull the slider over to the maximum number, 100, and you can see that it's denoising the signal nicely, but not doing anything with the resolution or the intensities as such, just creating a nice denoised image. If you are just interested in the pure raw data, you can leave it at 0, and this will not apply any kind of denoising on top. However, thanks to the Taustead method, we still have a really great contrast improvement already. There's one last option here, which is called Tau background suppression, and I will explain how that works again in a second. If I just deactivate this, you can see that we now also have the background back in the image, which by default is removed by Taustead, which is of course what you usually want. And this is thanks to the fact that we can now nicely separate, thanks to the FLIM part, which photons actually are coming from our dye and which photons are uncorrelated by the depletion laser and therefore are not coming from our fluorescence dye and can be treated as background and removed from the image. So how is this done? Let's have a little bit closer look into how that works. So for that, I'm moving out of the Taustead tab over into the Phasor tab. And here we have now the raw data of the acquisition that we just created. And immediately on the fly in the background, the system in Taustead already was creating a phasor of our two channels here. So every lifetime of every pixel is transferred into this phasor space down here, which is simply a different way of looking at your FLIM data. There will be another hands-on session tomorrow, which covers this part in more detail by my colleague Julia Osato. But for now, I just want to show to you how this is applied in the Taustead method. And what we see now here is all the lifetimes from the confocal as well as from the STED image. If we deactivate the STED lifetimes, this is the lifetime distribution in the phasor analysis of our confocal image. I can also select those, and then you can see those lifetimes are now highlighted in my intensity image up there. So we can see this cloud really corresponds to our confocal data. As soon as we activate the STED depletion laser in this channel over here, we are affecting the lifetimes, and we are creating a STED lifetime trajectory, which is what you can see here. So if I select now the confocal phasor and just look at the STED phasor, you can see that now they have a different distribution, which of course comes from the fact that now the depletion laser is a competing process to the normal fluorescence process and is changing its lifetime. What we're doing now in Taustead is the system in the background is looking for this trajectory in the phasor and has now a tool at hand which allows it to discriminate between the high resolution and the low resolution photons. So if we look at this now in more detail, I can select now these lifetimes with a gradient, and then you can see that actually now the ones that are here on the longer lifetime side are the ones with the higher resolution, which are usually more in the center of my nuclear pores, whereas the ones that are in the plot on the right-hand side, which is where the shorter wave lifetimes are the ones which have a lower resolution and which are usually at the periphery of my nuclear pores. So this is what is happening in Taustead in the background. We can really now on the single photon level discriminate between a high resolution and a low resolution photon. That is not all, however. We also have quite a significant portion of lifetimes which are not affected at all by the presence or absence of the depletion laser, and those are the ones which are uncorrelated and therefore are not derived from the dye that we are using. We can immediately identify them here in the phasor plot as having a different distribution, and if I change the colors now here, those can then simply be removed from my image, and this is what is done by this Tau background suppression button. Now with the Tau strength slider, what is happening is, I can illustrate that also if I change the color here now. The Tau strength slider is now simply a threshold that is removing or that is changing this gradient here. So by only displaying the high resolution photons, this is when I increase my Tau strength slider, I can improve my resolution even further, as you can see. If I keep all the photons, however, this is when I reduce the Tau strength slider, resolution goes down, but I am not removing as many photons anymore. Now, the default value of the Tau strength slider is chosen in a way that it is exactly at 50% between full depletion and no depletion at all. If you are looking at, or if you're thinking about the STED donut that we are actually creating here. So this is a nice illustration, I think, of how we are creating a Taustead image, how we are making use of the lifetime information in a purely physical way without any fitting to the data. We're just looking at the trajectory of the STED lifetimes and therefore can immediately separate where the high resolution photons are versus where the low resolution photons are. And by just applying a gradient, we can even in post-processing, if we want and if our photon count allows that, improve the resolution even further. On top of that, we can also immediately identify where the uncorrelated photons are, which are here in the background, not inside the nuclear pores, and can then simply remove them from the image. So this, in short, explains how Taustead works and how we can get from a confocal image to a Taustead image immediately. what we can actually also do, and this is one of the additional benefits of Taustead, is that we have all the FLIM raw data already acquired. So we can actually also not use the Phasor Taustead way of displaying our data, but the classical time-gated way as well, by just setting a strict time gate. And now let me just demonstrate this to you, that you can actually also now from the same raw data compare how it would look like under these settings with a classical time-gated acquisition. I will now just create a third channel where I want to use the same raw data now. So at the moment I have two identical channels here, and I can go back to this one in the middle and say that this should not be Taustead, but classical time-gated image. And here I have now the possibility, as it is in the classical gated STED case, to set a fixed time gate to simply remove certain photons based on their arrival time strictly. So here I would probably go to a rather low gate start, something like this. And this, if we look closer now, would be under the same conditions now, the results that you would get with a classical gated STED. And as you can see, you also, of course, get a nice resolution improvement if you compare it to confocal imaging. However, to really get a similar resolution as what we're able to get over here with Taustead and a similar signal-to-noise ratio, I would have to significantly increase actually the, first of all, the depletion laser power, and probably also the excitation laser power as well, which of course would then be much more harmful to my sample as the conditions that I'm using here right now. Okay, so that was a short introduction into how Taustead works. So now let's try to change a little bit our usual acquisition scheme. So if I go back now to my acquisition settings, we still have our confocal sequence to start with, and then we have our Taustead sequence. Now what I want to do is I want to decrease my depletion laser power and see what kind of resolution improvement I can still get. So in this case, I want to reduce it roughly by factor 3. So from 20, I will go to just 7% depletion laser power in this case. And then I will add another sequence where I want to go even lower, just 2%. And one last one. Sorry, I should have done this a different way, where I keep my settings as they are. So let's go back and just change the order. So here we just put 7, and here we put 2%. And the first one should stay at 0 for our confocal. I just want to make sure that I'm still in a good focus position here right now. And sorry, just quickly do a confocal scan. Yeah, still seems to be good. So actually can keep continuing with this cell here. And let's put back the settings. Okay. So 2%, 7%, and 20%. And now let's start. So now, of course, we have 4 channels that we are acquiring in a line-by-line sequential fashion. Sorry, I should move all of them to Taustead immediately, not to gated. So it simply remembers the settings that I had put here before. Now, of course, the acquisition takes longer because instead of 2 sequences, we are acquiring 4 in a line-by-line manner. So that then, of course, takes twice the amount of time. But still, you can see we get the Taustead result if I don't change the buttons down here immediately. And now we just wait until the acquisition is through. What we can already see from here. So this was our initial settings. This was at 7%, so 1/3 of the depletion laser power. And this was at just 2% depletion laser power, which is then just 1/10 of our initial setting. But now let's compare what we could have done with classical gated STED here. I will just add one more channel, which should be the gated one. 0.3 is a gate start. All right, and now let's look into our results here. So if we focus on these structures here, so even with 2%, we get a little bit of resolution improvement. Let's see if we can actually push that even a bit further with the Taustead strength slider. Sorry, that was a bit too much in this case. I should always look at the number of counts that I have here as well. But if I push it a little bit further to a little bit higher setting, I can actually start to resolve even with just 2% depletion laser power structures that I cannot resolve at all with confocal. With 7%, this looks already quite a lot better, even with the standard settings. And actually, if we compare that to our gated STED, the resolution is more or less similar. Let's try if we can optimize this a little bit further. So actually with just 1/3, if we compare these two, I can remove the other ones for now. So this is now gated STED at our initial 20% depletion laser power, and this is Taustead with just 1/3 of the depletion laser power, 7%. And as you can see, contrast is way better thanks to the possibility to remove the uncorrelated background due to the different lifetime that it has. And if we look at the resolution, it's more or less identical, I would argue, but with just 1/3 of the depletion laser power. And this is a nice example of how you can really benefit now from all the synergy of our Taustead systems. So we have already a really good and well-established STED system, but now with the combination of our fast FLIM system, we're able to really on the fly, not just capture the intensity information, but also the lifetime information of every single photon and every single pixel, and can really benefit now from this additional information and create this higher resolution at lower power and the higher contrast data with it. And with this, I want to finish this comparison here. I now want to show you one last thing with our Taustead before we move to another sample to also show you the multicolor capabilities. But please keep in mind that thanks to our Taustead approach, we can achieve similar or same resolution as with classical gated STED, but at 1/3 of the depletion laser power, which we will later on see in the live cell session, has really a lot of benefits for large volume acquisitions, also for acquiring living samples. Now, let's try to also use Taustead for improving the Z resolution as well. And for that, I will go back to my acquisition here. As before, we will start with a confocal sequence. I will delete the additional ones and just keep the last one here with my 20% depletion laser power. And now what I want to do is I want to switch over to an XZY acquisition mode. So for that, I quickly have to open my regular viewer again. Yes, it's okay. And in the confocal sequence, I want to set up this acquisition first briefly. So now we are doing an so-called XCY scan, which we can do thanks to our Z-Galvo. We can actually do a live cross-section scan, as you can see here, where we are seeing our cell in a cross-section, where you can then also see that, of course, in the XY direction, you always have a much higher resolution as in the Z direction. But one of the benefits of our Taustead system is that we can also improve the Z resolution. And this is what I want to demonstrate now to you. So let's go back to our settings. We start with confocal. Then we go to Taustead with our 20% depletion laser power. First, without any additional 3D resolution improvement. And then we create a third sequence. This time we have to do this between frames, where we now also want to improve the 3D resolution at the same time. For that, we actually have a slider which lets you freely tune how much of your depletion laser power you want to use for XY and how much for Z resolution improvement. And I'm putting now the setting here to 80%, which gives me the best compromise between X, Y, and Z resolution. So the smallest overall volume at the end of the day. I will uncheck this option for now and just comparing now my settings. So the last one is with Z resolution improvement. This should be, without. And the first one should be no STED at all. So now let's start this. And we start now with a normal confocal scan as before. And once this is finished, it will move to the second sequence, which at the moment is just black because it hasn't been acquired yet. Now we are in the second sequence, where we are applying Taustead already, however, without Z resolution improvement yet. So you see, if we look closer, we have a nice XY resolution improvement, but in Z, the resolution is not better as in regular confocal. And now as a third sequence, we also want to improve the Z resolution in this case. All right, so now it's finished. This is our data. Left side, pure confocal. In the middle, we have only XY resolution improvement, which gives me this famous pencil shape here. And on the right-hand side, we have now also a Z resolution plus an XY resolution improvement. So this nicely demonstrates, I think, the potential of Taustead for your fixed specimen. I will stop now with my part of the hands-on session here and hand back over to Mariano, who will show you also now how to do a dual color acquisition with Taustead. After that, I will come back and will show you how you can benefit from Taustead also for your live cell experiments now. So thank you and speak to you later.
Okay, thank you, Daniel. So now let's go to the multicolor part.
Should we have a look at a few questions in the meantime, Mariano?
Yeah, sure. You can answer the questions. I mean, I will just acquire. It will take some time. So if there is any additional questions.
So I saw there were a lot of questions or comments popping up in the chat. I haven't looked at them yet. I don't know if you did so far.
I looked at some of them, but I think some of them are mostly for you. So
okay. So maybe before you get ready, I'll try to answer two of them to not to respect also the time a little bit now. We will have more time at the end, as we said. So let me see, where did we start? So there's one question from Jessica about the Navigator. I think this is the first one. So I'll just start at the top now here. So Jessica is asking if in the Navigator there is an option to move the stage to a different region. Yes, so yes, you can do that. You can deselect the option to take an image when you double click somewhere else on the stage. I'll leave it at that. If you have more questions, please contact me later about that. But as there's so many more questions, so let's have a look at the second one.
There is actually
asking
quite a bit of discussion about exactly that question. So can you give a short hint on where to do that? How to disable the option?
So from the top of my head, it's just a right mouse click inside the Navigator window, and then you have a couple of options popping up there.
And the right option would be which one?
Yeah, I don't know how it's called exactly, but you can find it in there.
Okay.
That's what I can say now from the top of my head without sitting in front of a system right now. But I can come up with the exact name.
Sounds good enough for the moment, I think. When people have to know where to look, they usually find stuff.
Yes,
at least scientists.
Okay, second question from Susuban. What will affect if you increase the depletion laser power to more than 20%? Well, that is a question that goes into the direction of classical STED, which of course also is valid still for Taustead. So the more depletion laser power, the smaller your STED point spread function will be, therefore the higher the resolution. But at the cost of putting more light into your sample and at also collecting less photons, because your volume will be smaller, which means you deplete more, so there's less space for photons being emitted. But of course, still for Taustead, the more, as with classical STED, the more depletion laser power, the higher the resolution will be. So I hope that answered that question.
Cool.
I see you're ready, Mariano, so maybe...
Yes, so just I
now.
will do a small introduction about the sample. So the sample is not maybe as nice as the one that you show, but it's still good. So for now, we're just starting with just a classical multicolor setup using two dyes from two different spectra. So we have here the nucleus, the nuclear port stacked with a Alvarez star 580, and the mitochondria, this time tagged with the Alvarez star 635P. So two different windows, we do two different sequences. So what I have proceeded to do here is just a confocal image and a STED image of both panels. So we have 4 images in total. And here you can see that this image actually went better than expected. So I'm really happy with it. And as you said before, the Taustead image is immediately calculated. And for example, if I disable it, I think people will see like really how much it contributes to increasing the contrast in the image. You can really see it here clearly, how it really helps. And it's not, for example, as good as a time-gated. For example, this is a time-gated STED. So the time-gated more or less works well, but you don't take out this, I will say, out of focus background, and also some of the background that you can find. So it's really nice. So now what I will do here is just I will save this image here just to compare it more truthfully with the other ones. Or no, actually I can just do here. I can just increase the number of detectors like you did last time. Yeah, I don't know why it changed me the colors again, but okay. So again, if I don't have my eyes on the chat, so if someone has questions about what I'm doing, but it's not that complicated what I'm doing, I'll say. So for example, here you have a direct contrast between these two colors, Taustead and let's say normal confocal. And I can even now apply the time gated here just to see what is equivalent. And you see the performance and resolution, how nice it is. Okay. Okay, so, and this is just a two-color to label, so very simple, let's say, a slide to separate. Now we will go to something a little bit more exciting, and for the people that were in the morning in my workshop, I showed you how you can really easily and really nicely separate two dyes in the far red channel just with the lifetime. And the reason why we're doing actually this test mostly in the far red are because we also want to use these dyes for STED. So now I will use one slide that has one of the slides that I use in the morning. So the actin tagged with ATO 647N and the mitochondria tagged with a barrier star 635P. And we're trying to do not only color separation, but also STED at the same time, both dyes. So I'm just going now to change the sample, And in the meantime, you can ask questions, and I'm sure I will try, and Daniel will be happy to answer them. So.
Thanks, Mariano. There was one more question from Yanin, which I already tried to answer in the chat window. So question was, what is the Z resolution, which I did not mention. So depends, of course, on what kind of fluorophore and sample you're using, but let's say in an optimal case, the Z resolution will be better than 100 nanometer for Taustead. In general, I would say regarding the resolution, you also always have to keep in mind what is actually the structure of your protein that you're looking at. So that's, yeah, one nice thing of having the option to be able to tune your resolution, because you also don't want to, yeah, overdo it at the end of the day. So you don't want to tune yourself and your system to a resolution of 30 nanometer if your structure is 80 nanometer big, because that will then just lead to a yeah, loss of intensity at the end and lower signal to noise ratio. So if you always try to, yeah, balance that in an optimal way, that would be good, let's say. Of course, that's not always possible, because sometimes you simply don't know and you just want to be as small as possible. But if you have some knowledge already about that, use it. Mariano,
Yes, I'm back.
You still there? Okay.
Yes, I changed the slide now. So I will try now to find a good cell. And also I will need to adjust my settings. So of course, I already did my settings before. I just need them to apply them, which is, I would say, very useful, this feature. Okay, that's good. So now I just need to find for myself. And yeah, actually, one of the requests that I saw, it would be nice if we can have one fast live button in the main interface. Because to be honest, now that I'm using the Navigator a lot, it's very useful.
I agree, Mariano. Couldn't agree more.
Okay, so apparently this, let's see how this sample. Okay, so I think you can more or less see the mitochondria on the actin. Here, so. Okay, let's try like this. Let's see how it goes. So I'm doing STED, so of course I would like to have really small pixels. I can leave it at this. I can leave it at this. Precision rate, let's make it a little more. And then just need to check the step power. Okay. Now we can just switch onto the FALCON window, go to FastFlim. And we can see, I will say this line in the middle that you can see here is just because we are sharing via Zoom. So normally it doesn't happen, but it's something that we've seen apparently the system doesn't really like it. But anyway, here you can see that already by lifetime, we can separate these two dyes very easily. And anyway, in this sample, it's quite easy to distinguish the actin from the mitochondria. And now I will do on the right side the same, but with the STED image. We can just go have a look in the Phasor, how it looks like. So this Phasor that you can see here at the moment is the one of the STED image. We have two dyes, so we have two different clouds, if I may say. You can see here, and in the confocal image, you can see that the balance labeling in this dye is very nice. And as opposed to this morning, the overlapping of the structures is not very high. Hence the nice spatial separation that we can see here in the Phasor. So if I proceed to a very, let's say, quick, now let's say under the color separation. In the confocal image. So we can see that it works really nicely. And in the STED image, we'll proceed to do the same thing, but it will be more different. And we will use other kind of separation for the color. So we'll just need to wait for it to end. Yes. So of course it takes some time because I want to acquire as many photons as possible. And with this sample, I mean, the dyes were really, really, really good. And of course, with FLIM and with any microscopy technique, the more photons, the better. And it's a fixed sample, so we can take our time to make that decision. I even already tried to. Okay, so I hope it will end soon. Yeah, so it's done. So you can see in this morning in the confocal image using Phasor, I can switch very easily between the two dyes, so I have no problem there. So I will just put here acting just to save it for later. And then we can also confocal 20. And now we go to interesting part, so the STED image. So for the STED image, things are going to be a little bit more complicated because so far, what we had always is just the distribution over 2 points, as you can see here. So we had one dye with one lifetime, the other dye with the other lifetime, and then we can just, with a line, easily separate them. But now instead, we have, if I may say, a third component that influence our lifetime, that is the STED laser. So we'll have our two areas here, and then we'll have another area that we don't see it, but normally should be down here, if that corresponds to the depletion laser and also to the very short lifetimes. And these are the ones that we want to avoid collecting. So if I try to do the method that I applied this morning, you will see that it might work more or less quite well, but it's not as efficient as silent, I would say, to filter the other photons. So it's not really practical, or yeah, it works, but I'm not really that happy with the results. So what I tried to do the other time, and it more or less works well. So you have two solutions. Either the solution that I told you, where you can just do the circle and then you more or less select your area, which ideal as it is not the best one, but it's one that works pretty fine. You can see here, I'll say it's not so bad looking. Or what you can do, it's use another tool, because why using lines when we can use triangles? So in this case, I use a triangle to do my lifetime filtering. And I will say that the right bottom corner, I will say that's background. I don't want it. So I will just filter all this data. And for the other areas, I'll just change the color. So, okay, this is this. And the actin, I want it in green. And boom, I have my lifetime image, my STED lifetime separated image. Of course, the filtering is not as good as it was supposed to be. And here you can see in the overlapping structures, sometimes I have some kind of artifacts. But I think as a first approach, it works really nicely. And one thing that it might maybe improve in the future, and this is something that maybe we can discuss with Leica doing it, if they can want to implement it, is if we can have some play with this, let's say with the linearity of the intensity between the 2 points. So if we could play between the 2 points instead of just doing a linear increase or an exponential or a log one, then we might be able to unmix better and deal better with these small artifacts that we can see here. So this is one of the solutions that I will say works pretty fine, or we can try also to do it the traditional way as I already showed you. So okay, so here, and the other one here. So this is something I haven't really had time to, let's say, play around as much as I would like to. But yeah, any suggestions or commentaries will be great for this, because all of this is, let's say, quite new to me also. So yes. I don't know what you think about it, but at least I will say we can more or less easily separate the colors, and then for the rest, maybe we can do some post-processing to take out the noise or things like that. But at least the most important thing for me is that we can more or less see the big structures. We can see the different structures in the kernels recognize, and that is the most important takeaway for now. Maybe you had something more to add, Daniel, or?
Not for the moment, but thanks for the great presentation, Mariano. But just looking at the time, I think we should conclude this part for now.
So maybe just to avoid confusion here, this color separation, this is not included in what Leica is calling Taustead. So these are two different things. It's just that both are a combination of FLIM and STED, but it's a different approach to it. And right now we can't really combine those. We have actually one question here from Sebastian, who is asking, is there an output representation on the phasor plot, which parts are included or removed by tau processing?
Yeah, so thank you, Sebastian, for the question. This is, of course, goes into the direction of how can you know in the end in Taustead what you get as an end result. So that is, of course, yeah, an important control, I would say, to have. And there is no direct button that shows you inside the Taustead tab, okay, this is what is included in here. However, I can say that you can always, if you go yourself then to the Phasor, check it by yourself, let's say. So you can always, as the way we showed it now, me and Mariano, you can always create this gradient yourself and then sort of manually double check just for you as a control, if you would like to have that, what is included actually in the automatic result and what not. I mean, usually it's, or let's put it like this, the way the automatic one is designed is that you always get a good result, let's say reliably, without having to do anything manually. But of course, if you then want to dig deeper into it, you have all the raw data still at hand and can do that yourself.
Mm-hmm.
I hope that answered your question.
Should we get to the live cells then?
Yes, I think so.
Okay, so
I will just stop my sharing.
All right.
Maybe very short, as we had the questions. I guess there was one from Angelika Rück. If you can do Taustead at autofluorescence.
Yeah, thank you, Angelika, for the question. I actually read that. I thought it maybe takes a bit more time to answer in writing, so thanks for pointing it out again to me. So I would say in principle, yes, because it's fluorescence and that can be depleted. However, then on the other hand, I would say it depends, because autofluorescence is usually very diffuse, right? Not really specific to a certain structure or molecule even. So typically autofluorescence has many sources. I would say. And therefore, yeah, having an increased resolution in a diffuse signal doesn't really help an awful lot. However, having said that, there might be cases where it is beneficial. So in principle, it works, I would say.
Would be very beneficial to measure NADH inside mitochondria, for example, to get this signal. Would be very beneficial. But I'm not sure if it's really working because it's bleached very quickly, maybe.
Yeah.
I mean, then I would say, okay, it's worth giving it a try. I mean, again, having said that, so NADH, you need probably an infrared laser to excite that, right?
You need a UV laser, or when you do it with 2 photons, you need a 2 photon laser. So, for example, exciting at 760 nanometers or something like this.
Yeah.
Okay, with your white laser, you can excite at 380 or something.
Well, I mean, so at the moment, if we talk about Taustead and STED in general, we're talking about the visible range. So that is exclusively, let's say, with the white light laser.
Yes.
Or other visible laser lines. I mean, you could add an infrared laser to your STED system as well, but this is then definitely not a standard product, let's say, and would require some additional R&D input, like this. And then, yeah, I mean, on a system like that, it might work, yeah. But I don't have personal experience in that, so excuse me.
Anyhow, interesting. Yeah, thanks a lot for the presentation. It's very interesting.
Hello again, and welcome to our last hands-on session around our Tau-STED system today, where in this part I want to focus on how to use Tau-STED for live cell microscopy and how you can actually benefit from the advantages of Tau-STED that we have highlighted so far in long-term live cell experiments. In order to do that, I have a living sample here already mounted on the stage, which is a Nile red staining on HeLa cells. Nile red is a membrane binding dye, which is emitting in the red part of the spectrum. So I've added a little bit of Nile red to my living HeLa cells here. And now let's first try to get a confocal image. I will activate one of our white light laser lines and place it in an excitation range, which is optimal for Nile red. As I know the sample already, I can tell that we are fine with a rather low intensity here, as the signal is quite bright. And then I will also activate one of our hybrid SMD detectors, which are suitable for imaging with confocal and Taustead, as well as FLIM microscopy using our FALCON. As you have seen until now already, you can freely place the detection window of our detectors anywhere in the spectrum, and I will place it now so that it optimally detects all of the emission of Nile red, which unfortunately is not in our list of fluorophores in here yet, but I have selected SIR, silicon rhodamine here, which has a rather similar emission spectrum and which is what you see here at the moment. So now let's click on the live button to get a preview. You can see here are a couple of cells stained with Nile red, and all the membranes inside the cells are labeled here at the moment. This is just the current position that we're looking at right now. If you want to know how cells in the vicinity of our current position looks like, we can quickly move over into our Navigator window. And here, as you can see, I have beforehand created already a small overview using our spiral function, which, if you click on it, moves around our current position in a spiral way, as you can see, and keeps adding more and more neighboring positions until I press the stop button. So now we have a pretty good idea already of how our cells look like. They're not too dense here in this imaging dish. If you want to move into a particular position, you can also double click in here and the stage will move over there. But now I think we can keep continuing at this position over here, which looks quite okay to me. If I leave the Navigator window and go back into our main SP8, we are now, as you can see, at that current position. I want to zoom in now a bit closer to a few cells in here, so I can use our zoom in function. And now, as you can see, we are zoomed in to a little bit smaller field of view. And what I can also do here now on the SP8 is I don't have to acquire a rectangular field of view, which is what you would normally do. But in a time series, it's actually beneficial to limit the number of lines to a fewer ones, simply to have fast acquisition speed, but still at the same resolution. So here we have basically the complete freedom of how our format should look like. And I will keep the X format, but will reduce the number of lines that we are scanning now to around a third. So now if I click on live again, as you can see, we don't have a rectangular field of view anymore, but are looking at a strip scan. And I can change also and fine adjust the position now in here to go a little bit to the border of the cells and also adjust my Z position a little bit. And this is what we later on are going to image. Before I move over to the STED part, let me just quickly show you how we are using adaptive optics to actually perfectly optimize our objectives to the current sample that we have on the stage at the moment. And on our systems, we are doing that with a so-called motorized correction color, which is equipped on our STED objective. Right now I'm using a 93x glycerol STED white objective. All of our STED white objectives have an extremely high chromatic correction, which is of course necessary if you want a perfect Z alignment of different colors, especially in nanoscopy. And what we can do now with this objective is that we can change a correction color, which will actually change the physical properties of the objective, and which will then allow us to optimally adjust it to our sample. So I will go back in a live scan here. And if you are changing the slider over here, which is what I'm doing now, then you can see that the image that we're getting is changing and also the intensity is changing. And what I'm looking for now is that I'm looking for the setting, which actually gives me the highest intensity at the end. So this is somewhere around here. So this is making sure now that we have optimally adjusted our objective and our optics of our Taustead system to our sample. And I can simply do that, as I said, by choosing the setting which gives me the highest intensity, which at the same time is also the smallest point spread function and therefore the highest resolution. So let's close the mod core setting here for now. We have adjusted it already. And now what we want to do as a next step, we want to do STED, of course. So let's activate our STED button over here. As you can see, due to the emission spectrum of Nile red, we should use the 775 depletion laser, which I want to use at a rather low intensity, 15%, which will already give us a really good resolution improvement, hopefully. And still not putting too much light into our sample, which is of course important when we are talking about live cell microscopy. So I'm adding now 15% depletion laser power of the 775. I will not change the excitation laser power. But what I want to do now, as we of course now are in the super resolution range, I want to press the optimize XY format button over here, which is now changing the format to give me a correct pixel size now for my STED image, but still keeping our strip pattern that we have selected in the beginning with the same orientation, as you can see. So now everything is more or less set almost, but as this is a live sample, I want to acquire already a time series. So I will change the acquisition mode up here to an XYT mode for time. And then, as you can see, I get this additional time window down here. And if I click the minimize button, I can directly see what my time resolution is. And if I choose an appropriate number of line repetitions, so doing a few accumulations in this case, that gives me now, with the current settings that I have, a time resolution of roughly 1 frame every 2.5 seconds. Maybe let's add a bit more here. So now we are with 8 accumulations, 8 times line repetitions, which will give us a really nice signal at the end, roughly at a time resolution of 5 seconds per frame. And down here we can now set for how long we want to acquire. So let's start with a 2 minutes acquisition. If I activate this minimize button over here, that means that I will continuously acquire images without pauses in between. And now let's see how that looks like. If I press the start button, I can now immediately move over here into our FALCON window, which is where we will have our Taustead end results directly. And this is how it looks like. We're still acquiring the time series, but we're already seeing the individual frames as they're being acquired in the Taustead mode. So as you can see, I'm operating now inside our FALCON module that we have on the SP8, and I'm in the Taustead tab of FALCON, which then immediately recognizes that I'm using a depletion laser, so that this is a Taustead image and is immediately calculating the result on the fly from the phasor plot analysis. So this already looks quite promising. We already do see a nice resolution improvement, as you can see here. So now let's just wait until this time series is finished, and then we can adjust the end result accordingly. But what you can see already here is sometimes null red is also, or not sometimes, it's always labeling the mitochondria, but we actually have a few, I think, in this current field of view. We also have the nuclear membrane here and here, but we can nicely resolve the 2 membrane sides of the mitochondria in this area over here. So now we're almost at the end of our 2 minutes time series. And then we can look at the end result in more detail. Okay. Now we have our final result over here. I can restretch the lookup table a little bit. We can actually, from the same data, also compare the Taustead result that you see here with the gated STED, how a gated STED image would look like under the same conditions. I can, over here in the specialist settings, just copy my current channel, as I have acquired only one channel here for the moment. I'm just selecting the same one again. Now we see 2 channels over here, which for the moment are identical. And if I select the first one here again, I can move from the Taustead window over here on the left side to the time gated. And here also in post-processing, as we have all the data at hand, we can actually completely freely choose our time gate. So maybe 1 nanosecond time gate is a bit too much for the 775. So let's go to a really short one, 0.3 nanoseconds. And then the image is calculated with this new time gate settings immediately. So that's, again, one of the advantages of Taustead. We have all the raw data at hand and can even in post-processing optimize our settings. So now let's put them to a similar intensity. And what you can see already here is that we have achieved a significantly higher resolution, and also our contrast is a lot better, as we can not just improve the resolution thanks to the phasor plot, but we can also identify lifetimes which are uncorrelated with the STED depletion laser. So that means if you activate the depletion laser and certain lifetime components in your sample are not affected by it, that means that they're actually not coming from the dye that you're interested in. So you can treat them as background, as you can separate them also easily thanks to the phasor, which you will hear more about also tomorrow, and simply treat it as background. So that's done by the system automatically. There is a Tau background suppression slider or checkbox down here. And if you unselect that, you can also see how the image would look like when you include all the background components. But of course, normally you don't want to do that to have a nice contrast improvement as well. And now let's look at the whole time series, as we have living cells. Also, the intensity is not changing over time, as you can see, because we could really stay low with both our excitation laser and the depletion laser. I didn't have to increase the excitation laser as well as you would normally do with gated STED. So we can really nicely acquire also long time series. And in this case, as you remember from our settings, so the time resolution was 1 frame every 5 seconds. But of course, if you play a little bit with the settings, go for a little bit less repetitions, and maybe compensate with a little bit high laser power on the other hand, you can of course get to higher speeds also easily. In this case, I have acquired the data without any pause in between, which is of course also the most challenging setting. If you give the cells always some time to relax in between, you might easily be able to acquire even longer time series. Okay, I have switched over to another sample now. These are living HeLa cells that are stably transfected with a nanobody that is binding against GFP actin. GFP in particular has been a very challenging dye with conventional STED methods, simply because due to its rather low excitation wavelength, and also due to the fact that you have to use the 592 depletion laser in order to efficiently deplete GFP. If you compare that with the more redshifted depletion laser lines, the 592 puts a comparably high energy load into your cells. Now let's have a look what we can achieve here with Taustead, which, as we have learned so far, allows us to significantly reduce both the excitation, but most importantly also the depletion laser power. And that should be much more gentle and beneficial to our living cells expressing GFP here. So what we're looking at right now is a confocal live image of the actin GFP. I'm exciting at 488 at optimal wavelength for GFP thanks to our white lit laser, and I'm detecting in the emission range thanks to our spectral sliders here. So now let's again try to zoom into a little bit smaller region here with our zoom in function. And I can also fine adjust that to zoom in a little bit more, and also to optimize my Z position to a plane that I would like to image now in a time series. So I will leave it now at this setting and then immediately switch over to the STED panel. As I have mentioned, for GFP, I have to use the 592 depletion laser line, but I want to use it at a really low power, just 5%. And I want to see how much I can improve now my result compared to confocal microscopy. On the other hand, I will not change the excitation laser power and leave it at the same level that I have used for confocal imaging over here. In order to have a high time resolution, I want to restrict myself also to just 2 line repetitions now in this case. And of course, I have to change my pixel format in order to give me a small enough pixel size to collect the full resolution that we are going to generate now here. So with these given settings, I end up at a time resolution of a little bit more than 1 second, 1.3 seconds per frame. And I want to image now my cell for around 1 minute continuously without pauses in between the individual frames, which is what I'm setting up now here. And now let's just hit the start button and switch over to our FALCON window, where we can immediately see the Taustead result, as you have seen already in the other examples before. What we can immediately appreciate here is the nice contrast improvement thanks to the Taustead and thanks to the fact that we can specifically identify the background components and remove them from the image. And also, even though we're just using 5% depletion laser power, we already have a nice resolution improvement, which we can then also compare later on with the confocal image and also with the time-gated STED image. For now, let's just wait until the time series is acquired, and at the end we can compare them side by side with each other. Okay, the 1 minute is over. My data has been acquired now, and I want to first create also a sequence which represents the image as a time-gated data set. I will use a rather conservative time gate with 1 nanosecond gate start, which I think is required for GFP. One of the additional benefits of FALCON is that we have acquired all the photon arrival times already in our raw data, which means that we can actually set our time gating in post-processing the way we like and the way which would be optimal for our sample. And I can actually in post-processing change now the value to another one without having to acquire a new data set. So this is now the comparison. On the left side I have Taustead, and on the right side I have the equivalent of how it would look like in the time-gated STED acquisition. So now let's just save these 2 channels as an intensity image, and I will go back now and just acquire 1 additional frame without STED, just in regular confocal, in order to have a comparison. All right, so this is now my pure confocal frame without any STED laser power. And now we'll just open a second viewer here, where we can add both our Taustead and time-gated STED. And let's do that for a third one as well. If we press on this small link button, all the changes that I'm doing will be applied automatically to all the sequences. And here, this one should be now my time-gated STED, and this last one my Taustead image. All right, so this is the end result now. I think if you look at the last one here, which was our Taustead image, you can nicely see that we created a resolution improvement. We see some smaller fibers, especially down here and also in this region. If you're comparing that with the gated STED image, and of course, something that is very striking is that the contrast is improved significantly. On the other hand, if you compare the traditional gated STED with just 5% depletion laser power, we hardly see a resolution improvement over regular confocal imaging. So to really get an improvement with time gating, with GFP and the 592 depletion laser, we should have to work with at least 10 or 15% so 2 or 3 times higher depletion laser powers in order to actually see a significant improvement in resolution. Because now if you're actually comparing some regions in here, of course you do see sometimes little smaller structures, but there's, as I mentioned, hardly an improvement visible. Plus we are losing a lot of photons because of our smaller point spread function, which makes then the image appear a lot noisier. So all of this looks better in the Taustead image, higher contrast and higher resolution. So let's just go through the time series here now and see how our HeLa cell is actually moving over time. And now we really have an additional information which classically with STED microscopy was challenging to achieve. Getting a good resolution improvement on a fixed sample is something that you can easily get with the appropriate settings and labelings in STED microscopy. However, to also get dynamics at this high temporal resolution, 1 frame per second, has been really challenging in the past. But this is something that we can now really use and investigate with when we talk about Taustead. Now, as a last point here, let's see how much photo damage we have actually introduced to our cell here now. So if I go now over here to the Quantify tab, I can measure the intensity over the course of our time series. I did not rescale the intensities when I saved this as from FLIM as an intensity-based image. So the grayscale numbers that we still have here actually represent the numbers of photons that have been collected initially, which means I should rescale my y-axis now here. And if I do that, we can see that when we started this acquisition, we had an intensity over the whole image of around 2.4, which then reduced slightly to around 2, as we can see here. But then from there on, it actually remained pretty stably throughout our time series, even though we were acquiring at a really high temporal resolution and acquired in total 46 frames. So I hope this shows you the benefits of Taustead, that we really can image, especially in live set situation, much more gently than what was possible before with gated STED. And we can still achieve a high resolution and high contrast with this method without having to introduce a lot of light into our sample or to do a lot of repetitions or slow scanning. So with this, we're at the end of our hands-on session around Taustead. I hope you enjoyed it as much as we did, and I'm looking forward to our question and answer session, which is starting now. Thank you very much and goodbye.